Hello there guys, it's Krishna here and welcome to our next class for the third unit. This is a class that is part of the high school and 11th high school. Today we're going to be working on the subject Physics 2 and on weekend number 24. So let's go over our presentation. Remember to have your notebook with you in order to make today's summary. Keep in mind to add the following parts to your summary: date, ending mind, title, the summary itself, of course, and some extra decoration to it. Today we are going to work on topic 6.07, wave phenomena, and the ending mind for today's topic is the following. Describe the concepts of interference and diffraction of waves, solve problems involving wave interference, and explore other wave phenomena. Alright, so make sure to keep track of the ending mind in the summary for today. Let me give you a small summary of the activities that you need to accomplish. So first, you need to watch this YouTube video and of course make a summary in your notebook. Number 2, read topic 6.07 and complement your summary. I suggest that you especially focus on page number 3. Then complete the assessment for topic 6.07 in Agilex. I suggest that you review a little bit the topic before you take the assessment, and in case you have any questions related to it, you can always contact me in WhatsApp. I will be more than glad to help you out right there. Alright, so just like I mentioned before, our topic for today is wave phenomena. So, in the image that you can see right here is part of the experiments that were made in order to generate evidence about the way light will travel. Because remember that we have studied before that light travels through waves. But how did people come to this conclusion? Well, it's very simple. Just like you can see right over here, we have like two different panels. Right over the panel that is right in the front, there are a couple of holes where actually can go through. So when light goes through these holes, then you are going to notice that a different image is going to be projected in the back. So, or of course in the front of the panel. So depending on what location we are going to locate our bulb at, we are going to get a different image. So for example, the closest it gets, then the farthest from the center the light rays are going to be projected to. But the farthest they are from the first panel, then the closer they are going to get from each other. Alright, so let's continue with a little bit more content. We need to remember a couple of important concepts, such as wavelength and frequency. We haven't received a physics lesson for 2 weeks, I guess. So I really suggest that you go back to your notes and actually check each one of the parts of the waves that we have studied in previous lessons, because it is very important that you have them in mind, and of course that each one of these concepts are very fresh and clear in your mind, so it will help you out to understand today's topic. Okay, let's continue. So Thomas Young, in the years from 1973 to 1829, observed a pattern in light after he passed light beams through two slits. His experience, in combination with Christian Huygens' principle, gave evidence about considering light traveling through waves. Just like I was mentioning, you have two panels, you have a light bulb, you're going to project light through the first panel with a couple of holes, and then you are going to observe the behavior of light. Alright, let's go over some key vocabulary. So first of all, we have interference, and it is the effect of similar waves passing through the same region. The total amplitude will be the sum of the amplitude of both waves. Alright, in other words, let's suppose that we have two sounds that are very similar, of course talking about wavelength. So if they go over the same medium in the same place and time, what's going to happen is that there is going to be a distortion in the waves. So that will cause that humans will perceive them in a different way, which in some cases, if the a sound comes from the same, let's say from the same object, and the sound is very similar, then a similar sound is going to be created, but with a higher wavelength. And of course, we're going to perceive them as a louder sound. But in case both sounds are similar in wavelengths, but they come from different objects, and of course the sounds are somehow different, then the resulting sound is going to be different from what was usually created at first. We have the principle of superposition. It is a principle applied to two waves traveling in the same space and time. So, many things can happen when two waves are traveling in the same medium, space, and time. And this might be a little bit confusing at first, so I'm going to explain them and word it out the best way I can. And of course, I will ask you to go to Agilex. There you will find some simulations that will help you a lot to understand that better. All right. So, of course, if you need to, you can repeat this section of the video a couple of times until you fully understand. And of course, support your learning with the simulations that you have in Agilex. So let's go with the first one. We have superposition of waves in opposite directions. So they travel through each other without disrupting their shape or direction. So let's suppose that we have one wave that is going from left to right, and we have one wave that is coming from right to left. But the first one is a little bit bigger than the second one. And of course, just like we are expressing right now, they are traveling in opposite directions. So what happens when they actually touch each other or they pass by each other? Well, actually nothing is going to happen as long as the medium where they are traveling is flexible. So basically they are going to continue in the same direction. So the one that is coming from left to right, it's going to continue with its path. And the one that is coming from right to left is going to continue with the same path. So in the exact moment when they get together, they're just going to travel through each other, but they will not be disrupted. That's the first thing that can happen when two waves collide. Let's continue with the next one. We have constructive and destructive interference. It's a little bit simpler to analyze. So when two waves are in phase, which means that they have the same amplitude and they are going in the same direction, they will sum up their amplitude, right? So two similar waves that are that have the same amplitude and traveling in the same direction, they will duplicate their size, let's say. Okay, they will grow bigger, and the result will be double the amplitude of the original waves. When two waves have opposite phase, which means that they have the same amplitude but the exact opposite angle, which will be 180 degrees, they will cancel each other out. So we have to remember that when we're talking about waves, there is an equilibrium line, which is right in the middle of the waves, okay? So basically, when two waves are going to disrupt each other, or they are going to destroy each other, is when one is going up while the other one is going down. But they have the same amplitude. Let's say the wave that is at the top has 2 centimeters, and the wave that is at the bottom has 2 centimeters as well. So of course, if they are traveling at the same place and time, they're going to end up eliminating each other. So constructive, if they travel exactly in the same direction and time, like let's say both of them are traveling at the top at the same time and they're both traveling at the bottom at the same time. They will duplicate each other. Okay, let's continue. Of course, we continue with some key vocabulary and we continue with the principles of superposition. So the next one, two sine waves traveling in opposite directions create a standing wave. So when two groups of waves travel with the same amplitude, travel in opposite directions continually, in the point of intersection will be created a wave that stands still and oscillates up and down. It is called a standing wave. Alright, so let's suppose that we have two groups of waves, and they are apart from each other by a distance of 10 centimeters. And there is something that is causing those waves to continue forming. Alright, so they continue forming and forming, and there will be a specific point where they are going to get together. So since they are separated by 10 centimeters, right in the middle, we are going to have a distance of 5 centimeters apart from in each of the forming waves, okay? So in those 5 centimeters, there are going to be waves that are going to be constantly interacting within each other. But what happens is that when many waves are being created and they are interacting at a central point, remembering that they have the same, let's say, the same amplitude, then there is going to be one wave at that specific 5 centimeter measure that is going to be staying still. It is not going to travel right, it is not going to travel left, it is going to stay in that specific point, and it is just going to oscillate up and down. Alright, and of course, going back to this topic, we have two important terms right there, which are the antinodes, which are locations with maximum displacement. We have nodes, locations with no displacement. Okay, so both of these terms are related to the standing wave that just goes up and down. Alright, and lastly we have two sine waves with different frequency or different beats. So two waves with the same amplitude are traveling in the same direction. Both waves have different frequencies and wavelengths. Their recombination causes the resulting wave amplitude to increase and decrease constantly. Alright, so this one is very interesting to analyze as well. So basically what happens is that they are going to have the same amplitude, the waves that we are analyzing. But let's say that one is going to travel faster than the other. So what happens right there? So when they start recombining, you are going to notice that there are some sections in the resulting wave that are going to be smaller than others. And usually these waves are going to behave in the following way. At first, you are going to get some resulting waves that are going to have a very small amplitude. They are going to continue expanding until they reach the maximum amplitude that they can go through. So we start from little to the maximum amplitude, and then we are going to come back to the littlest amplitude that they can form. All right, that happens specifically because the differences in beats. All right, so one more time, I suggest that you go to the simulations that you have in Agilex because they are quite helpful, and I consider they are going to really help you out a lot to understand the behavior of the principle of superposition. All right, so just like I was mentioning, go to page number 1 in the principle of superposition and observe the simulations. All right, now let's go over some important terms. We have diffraction. So it is the bending of waves around an obstacle. And this is a term that we already analyzed before. Just like when someone is speaking around the corner, then you can notice that the waves are going to diffract, or they have to go through a certain object, or they have to go around the corner in order to be listened by someone else. We have interference patterns, and they are obtained from coherent radiation. This happens when two waves have a constant phase relationship and have the same wavelengths. In a screen, bright and dark bands will appear. Alright, so interference patterns, specifically when we're talking about screens, small distortion is going to be generated right there. We have the double slit interference equation, which is expressed right here. And probably you can notice that we have some different letters that we haven't had before, as well as some different symbols. So let's go over the meaning of each one of these letters and symbols. So the first one, this one is going to be the wavelength in meters. Then letter D is going to be the distance between the slits. And then we have letter X is the distance from the central maximum to the first bright fringe. And lastly, we have letter L, which is the distance from the double slit barrier to the screen. Alright, so it's very important that you keep track of these definitions and terms, so later on when you start solving a couple of problems, you can identify them easily and go ahead and apply the formula. Just like you can notice, the formula is quite simple, so just in case we need to find any of the letters specified right there. For example, let's suppose that we want to find the distance between the slits. So we can simply rearrange a little bit the formula and of course use it later on to apply it in the problem we're solving. Alright, so we have some more simulations. So go to page number 1 and run the diffraction and interference simulation to understand better the behavior of waves. Once you have finished with that simulation, please come back to the class so we can continue with the video. Alright, now we are going to go with some application problems. Now, finally, after we have analyzed a lot of theory, we're going to go over some problems that we can actually complete with the formulas and everything. So it's problem number 1, double slit interference. A beam of red light is made to pass through two slits that are 4.0 e minus 3 meters apart. On a screen 2.0 meters away from the slits, an interference pattern appears, with bands of light separated by 1.8 e minus 4 meters. What is the wavelength of the light? Alright, so remember that at first we need to write down our givens. So what are the givens that we have? So the first one, which will be the distance between the slits, would equal 4.0 e minus 3 meters. Alright, we already have L, which is the distance from the double slit barrier to the screen. And that is going to be of 2.0 meters. Lastly, we have letter X, which will stand for the distance from the central maximum to the first bright fringe. What are they asking for? They are asking for the wavelength. Alright, so we have our formula right over here. This is the based formula. So basically we're just going to move the distance from left to right. Since it is dividing, then it will be multiplying. Then of course we are going to write down all of our data inside the formula. And lastly, we are going to find that the wavelength at the end is going to be of 3.6 e minus 7 meters. Probably the terms are a little bit complicated to remember at first, but once you have practice and you get the hint out of it, it's going to be way easier to complete them. Let's go over another problem. Problem number 2. So two slits are cut 1.0 e minus 4 meters apart in an opaque object and are illuminated with monochromatic light. If the first order bright line, X, on the screen 2 meters away is 1 e minus 2 meters from the screen, what is the wavelength of the light used? If the visible light has wavelengths between 5 e minus 7 meters and 7 e minus 7 meters, is the light used visible? Alright, so let's go over right over here. And one more time, you need to list the givens that you have from the problem. So right now we have letter D, which will equal 1 e minus 4 meters, we have letter L, 2 meters, and letter X, 1 e minus 2 meters. And one more time, at first they are asking us for the wavelength, so we are just going to use the formula that we used from the previous problem. We are going to replace the data that we already gathered from the givens. We are going to replace them in our formula, and we are going to operate them. So at the end, the result of the wavelength we are going to get is 5.0 e minus 7 meters. Alright, and lastly, let's go back to the last question that was written down here. If the visible light has wavelengths between 5 e minus 7 meters and 7 e minus 7 meters, is the light used visible? So the answer will be yes, it will actually be visible because it is between the ranges of visible light. Alright, oh, it's right over here, I didn't remember about it. Alright, so let's continue problem number 3. Red light with a wavelength of 6.64 e minus 7 meters is used in Young's experiment with the slits separated by a distance of 1.20 e minus 4 meters. The screen is located at the distance from the slits of 2.75 meters. Find the distance on the screen between the central bright fringe and the first bright fringe. Alright, so now things have changed a little bit, just like you can notice, we already have our wavelength. Also we have the distance between the slits. We also have L, which is the distance from the double slit barrier to the screen. But right now what they are asking us for is for X, which is the distance from the central maximum to the first bright fringe. So one more time, we just have to rearrange a little bit the formula, which at the end it's going to result in this one. We have to replace the data that we gather from the givens and from the problem inside our formula. We are going to operate it, and right after we synthesize our result a little bit more, we are going to get that X will equal 0.0152 meters. And that'll be it. So usually you can notice, usually physics is not complicated, as long as you know the terminology, you have all of the concepts clear in your mind, you list the givens, reorder the formula, and substitute the values and operate them. It's pretty simple. So that's it for today's topic, guys. Thank you a lot for coming. And just in case you're having problems when understanding any of the problems that I have explained here, or when completing any of the activities in Agilex, you can always let me know in WhatsApp. I will be more than glad to help you out right there. So goodbye, guys. Always take care, and I will see you around.